of the bags scanned. So here you can also see one of the bags. So we have a state-of-the-art object detector which is trained for fixed number of classes. For example, in this case, it is trained for gun, knife, and scissor. Now we need to add more class to the already trained detector. The best approach would be the incremental learning framework. So if we have suppose new requirement to add new classes, either we can retrain the network again, or we can go in the incremental setting framework. So the idea is if we go for incremental learning, then it will save our time. So here you can see, so new categories are added here: the bomb and the plier and the spray. These all are in the incremental learning framework. But the issue is like, and so for example, now the model is already trained for the 10 classes, but one new class come, we say which we want to add to the model, but for that we need data. So for example, that new class needs thousands of images. To scan those thousands of images is a very tedious task, because you need manual effort to scan those bags. So it's very difficult. Second issue is like, if you develop a model for one of the machines, probably the new machine would have some different color format. There you need some sort of domain adaptation between these models. All the publicly available data set have limited categories, because X-ray images for baggage are not very publicly available. Few of the categories are available. In case requirement comes for something like Matchbox, but it's not available in the public data set, so we cannot use that public data set directly. The solutions for these problems is like, we capture the threat object. For example, we want to detect seizure, so we capture the threat object independently. We should have a set of benign bags, say 1000 bags, and we should fuse those objects into the bags, and we can generate n number of images. So, and then we can recolor those images using some AI based coloring network. So here you can see these are the three threat objects. One is seizure, this is the box cutter, other is the knife. So in one of the bags, we are placing all three objects at different locations and different orientations. In second bag, we are placing three knives of the same type at different orientation and location. And the third bag, we are placing overlap of a scissor and a box cutter at this place. So this way, if we have say limited number of benign bags and we have threat objects scanned separately, we can generate large number of bags to train our model in incremental learning framework. Other thing which we do is material discrimination. So here in this image, you can see there are two packets here which are potentially explosive. We have a network which we train to detect these explosives here, right? Here also you can see these two are explosive in reality, but this is a benign items. Our network detects these two explosive with high confidence. This benign item also is an explosive with low confidence. But when sort of thresholding, it also highlights the explosive. This becomes false positive in our case. So this is one of the crucial applications which we develop for X-rays to identify the threat items which lie in the organic range and which are actually explosives. The second product for us is under vehicle scanning system. So this you can see here there is a pit on the road and the camera that is installed inside this pit. I can show you video if it's working there. Can you move the slide? Yeah. So the underside of the car is scanned in this way. Can you move the next slide? So, yeah, that's all. So this type of image is generated for the underside of the car. There is a small slit in that setup. So only you get frame by frame data, and these frames are stitched together to generate the final image here. So now we generate a data set of reference images, and whenever a target image comes, we pick a best reference image for the target image, and then we compare the target with the reference image to detect if something, some foreign object is attached to the underside of the car. So, why it's not working? Can you move? Like it's not working. That's it. So we do some sort of image-based algorithms and depth-based algorithm to detect the potential region where there's some foreign object is attached. Here you could see the large mean that there is something which could be a foreign object. Next. Yeah. Yeah.
For example,
Yeah.
So inside the car, maybe the one car was very old and it was broken and it's just taken care of by manufacturers. So how we decide that this is the foreign object and this is not?
Yeah, so there are reference car database. So we first select the brand, which brand we need. So there are two type of solution for this problem.
Same brand.
Mm-hmm.
My car is very old.
Mm-hmm.
There are some renovations, so they have added something at the bottom of the car.
Mm-hmm.
Maybe it looks like foreign object.
Yeah, true. But that would be a different card. So when we do sort of matching algorithm from the reference image, we'll pick the image which is more like to the target car. So there is a algorithm to pick the particular car from the database. So these could be the, after applying some sort of image processing or morphological operation, these are the potential threat objects. Based on the size, we can, so this is just to scan the underside of the car, typically install a so the high security venues like sort of parliament.
Cars of all types will come.
Yeah, so we have to maintain the database for different cars.
All types.
Yes, yes. So it depends. There are two type of solutions to this problem. If the venue is like only no, that is what I'm saying. There's two type of solutions. So in some particular venues, for example, Parliament, only few cars are supposed to allowed. So once those are coming, so we know the particular car. We have LP number. We know the LP number. Scan the LP number. We save that car in the database. For example, one car of one particular MP is coming all the time. So we have to scan that particular car. That car is regularly coming to that venue. So we scan the LP number. We'll get the license number. We actually pick only that reference image from the database. Okay. So first we'll check for the vehicle DB whether we have the license plate corresponding in our database. If we do not have, then we'll go for the type DB, particular type car. For one of the cases, but if it's not matching with the LP, then we go for the car type. Okay, sure. Yeah. Yeah. The next, yeah. So here we can, after applying some sort of thresholding, we can detect these are the foreign object attached to the car. So the question is, how are you using ML in this particular problem? So for example, we're doing sort of, we have target image, we have reference image, the speed of the car can vary, the car can come at some angle, so we have to do registration. So we are applying some sort of registration there. We have to detect the object, so we have to either use some image based feature or we should use some sort of depth based feature. When something is attached to the body, then depth will change. So that's why we are using RGBD based level, second level of inferencing. Car model detection, we are doing that. And mask generation, a lot of red region you would have seen outside the car. That is because the depth is different there. So we generate a mask of the car to remove that particular region. So the last product is Okean. The Okean is an advanced video analytics platform. It's a platform used for video analysis and alert generation and powered by CPU, GPU, and AI based accelerators. It has the capabilities of high scale and modular software architecture. Yeah, so if I can show you, this is typical surveillance view, which we assume, okay, everything is properly separated. We can see humans there, but this is not a real view. Can you move to the next slide? That was the ideal view. Typically, the views are like this. There are people in the far field also, which are very difficult to detect. Next slide. Same here also, there is a lot of gathering there, but you can't identify because of the low resolution at that level. Next slide. So here you can see the elimination problems. Foggy condition is there. So here the detection become very difficult. These are the challenges which we face. So these are the products which we are developing in Okean. Next, yeah. One is traffic law enforcement. In traffic law enforcement, we are working with overspeeding, no helmet detection, triple rider, and this is a red light violation and the no seat belt. In vehicle incident detection system, we are looking whether the cars are taking wrong turn or they are moving in the wrong lane, like opposite direction. And is there a queue developed on the road and some sort of accident? In PP also, we are doing analysis for whether the person is wearing jackets, shoes, helmets or gloves. In smart and safe city, the analytics are typically the crowd estimation, the crowd density estimation, fire and smoke, the sort of fighting, people are fighting that we have to detect, person attribute recognition, some sort of anomaly if it's there in the sea. Yeah. The key process for all VA is first detection. We should be able to detect people or objects carefully. Then again, if we are able to detect, we should track them properly. Re-ID, activity recognition, and the crowd dynamics. The main challenges which we face is like here detection will become very difficult when because the view is covering that far field also. So in these cases, we face challenges. Next. Here you can see we can detect the people, but few of the people are partially occluded. This again it's very difficult to detect these few people. Again, in the condition the glaring effect, lighting effect, all these create a lot of issues. Here you could see the scene has changed when there is sort of rain. So again, that's become difficult. Now I can show one particular scene to you. Next. So here you can see back. The same scene after 2 minutes, 4 minutes, or 6 minutes. So because of fog, nothing is visible here. So what if we are running analytics at this level, they are not giving performance at this particular level. Tracking. Yeah, so tracking challenges is one is Re-ID challenge. Here you can see one person is there, it goes out of the frame, then it again comes into the frame. So the idea is we should preserve the identity of this person. We should not assign new ID. So this type of issues we face in our work. Again, tracking. Here all the policemen are wearing the similar type of dress. To assign a particular ID to one particular policeman is very difficult. As ID gets switched, it's very difficult here. Next. In VIDS, vehicle incident detection system, we know there is an accident happened here, but because it's very far field from the camera, it's very far from the camera, it's very difficult to identify this. And some challenging scenario which we face in crowd dynamics is like the lighting change very fast, fog issues are there. Back. So here we have to, yeah, just 1 minute, last, okay. So you can see the crowd. So the idea is to count this crowd. So it's very difficult. We have to apply some sort of algorithms to, give some sort of approximate estimate of the number of people in the frame. Next. The problem use cases in VA are, as we all know, domain adaptation. Whatever you will develop for one particular view should work in general also. Class incremental learning also. Self-supervised learning, model compression, and out-of-the distribution detection. And since we do not have data for many of the applications, then we want to generate some sort of synthetic data also. Yeah, thank you. Thank you very much.
Thank you for the wonderful introduction session 1. I request Subramaniam Munara sir to facilitate the Wayhunt technology. Thank you, sir.
So good afternoon, everyone. We have Ms. Nikita Pinto here for the keynote this afternoon. So let me just briefly introduce Nikita Pinto. Nikita Pinto is a Senior Artificial Intelligence Academic Liaison for Asia Pacific at MathWorks. She is interested in understanding AI techniques and applying them to scientific and engineering problems. She works with educators, researchers, and students across India, China, Japan, Korea, Singapore, and Australia to help them incorporate AI along with their domain expertise. Nikita has a deep-seated fascination with the rapidly evolving landscape of generative AI and its potential to revolutionize research in engineering and science. She has a master's degree from IIT Madras, where she worked on applying statistical signal processing to underwater acoustics. She has worked on interdisciplinary projects with international collaborators, government research labs, and independent researchers. CVIP warmly welcomes you to the keynote.
Thank you, ma'am. Thank you, everyone. A very warm welcome to this talk on AI-driven computer vision for engineered systems. My name is Nikita, and I'm from a company called MathWorks, which makes the product MATLAB and Simulink. So some of you came to our session yesterday where we did a hands-on session. And we showed a couple of practical things such as AI modeling, working between MATLAB and Python, explainable AI, which is a common topic nowadays, as well as hardware deployment. So today, I know the last 2 days, we've seen a lot of talks on some amazing topics. I also learned a lot from sitting in these sessions. What I'm going to talk you through is some of the experience we see working with industry as well as with researchers who are interested in translating their research and taking it out into the field. So let me figure out how to run this. Okay, yeah. So some quick examples, okay, around where computer vision and AI-based computer vision can be used. Here you can see for robotics development, to develop bio-inspired robots, you need to monitor the system. And this monitoring can happen using motion sensors, but crucially using computer vision as well. Another nice example, very important, we believe, is on detecting whether or not the human being is sleepy or they are awake and alert. And these can then supply driver alerts through the automated driving assistance in cars. A third one, very important, you would have read the news in the last year, right? There have been a lot of, I would say, issues with certain airplanes made by certain companies. And that's why the importance of automatic defect detection at multiple stages of the manufacturing and assembly process are very important. All of these are done using computer vision. The last one is very interesting. It's how do we, this is based out of the US, but how do we enable our farmers to have large-scale farming operations, right? There has to be some sort of assistance in the form of autonomous systems as well as crop health monitoring and so on. A couple more. One that we're all familiar with is automated driving and driver assistance. So here you can see BMW has used computer vision and they've integrated with ROS to do this. Pilotless helicopters. I don't know how many of you, I'm based out of Bangalore, and then we've got this new initiative that's coming up where there are going to be these helicopters that take you from wherever you are to the airport, because it takes a very long time otherwise, right? So maybe in the future, you might see a little bit of autonomy, autonomous navigation with these systems. Very crucially in healthcare, and I'll talk about this a little more, but computer vision for medical diagnosis. And here you can see it's telling you where the issue is present, but I'll come and talk about this a little more when we're looking at explainability. Last one, of course, this is an area of special interest for me. I used to work in underwater acoustics, and underwater monitoring can be very tricky because the whole physics of the environment is different. And so can we use a combination of sound, a pressure wave, as well as computer vision? Okay. So I know in my title, I had the term engineered systems. So let's talk about what is an engineered systems. And here you can see there are these three sets of equations. You have Newton's laws, the laws of thermodynamics, and Maxwell's equations, which basically govern how systems move, how they transmit and receive signals, and how they transform or how they generate or utilize energy. So these are what we think of as engineered systems. And how do we take these equations? A lot of equations in engineered systems as well as in AI, which you're probably familiar with. And how do we build a system that is working in real time and impacting human lives? So here you can see an AI-based system to help control a prosthesis. So what's needed for this is some kind of AI-driven system design. So in AI-driven system design, there is a standard workflow. This is an oversimplification, but these are the basic steps. You start out with data preparation. So you get your data set ready, pre-processing if you need domain knowledge and so on. You then move to system modeling where you're actually trying out different combinations like Professor Chandrasekhar was saying. the biggest issue is what are the right parameters? What is the right architecture for my model, right? So a lot of experimentation happens here. And once your AI model is ready, so the AI model that you saw on the last slide took muscle signals and then translated them to actuate the drummer's prosthesis. That was done through deploying it on embedded hardware. So you may have the best algorithm in the world, but when you need to build a product or you need to build a system, it has to integrate with the rest of your system. And finally, part of that, integrating with the rest of the system could also mean deployment, putting it onto edge devices. And we saw some of this. We did a demo yesterday. So these are your 4 stages. And there are some huge practical challenges that come up in each stage. So I'm going to talk through a few of them. And we look at what are some of these challenges as well as how can we sort of navigate them. I'll start out with the data part. For practical purposes, how can I ensure high quality training data? Okay. So you may be working with data that's across multiple formats. It may be image, video. I know a lot of you are working on that, but you can also get into medical data, into data from geoscience, renewable energy, and so on. Okay. So in that case, you may want to build up a data set, which is where the idea of automated labeling comes into picture. It may be for autonomous driving, here where you're fusing camera data as well as LiDAR and radar data. Medical imaging, and here medical image segmentation actually using AI. Here's an example of an automated labeler. So let's say I'm built up a new object detection algorithm and I want to compare it to some of the state of the art, but I want to do it in a country like India. Do you think that this models and this data set from the US will guarantee results for me in India? No, right? We need to look at an Indian data set and we need to build it up so that we can test our algorithms. So let's take an example of that. I'm trying to do sky and road segmentation here, and I'm doing it using simple logic. I'm using basic image processing to distinguish between the road and the sky. And this image processing algorithm is my road and sky segmentation, very simple. What I'm doing now is I've brought in a data set and I'm asking it to automate the labeling based on the pixel values. And it's doing an okay job it's doing a great job for the sky, but a terrible job for the road. Okay. And here I have 3 images. I could as well have had 1,000 images. What I can then do is go and modify the ground truth. So I can come and fill in these areas that were not captured by my automated algorithm. When I come to the third one, I'll see that when I try automating it, it's overcorrecting. It's taking regions that don't really belong in the ground truth for road. So I can just go and modify that and clear out these excess areas. Okay. So here, 3 images, like I said, 1,000 images, 10,000 images, and you can apply this to your entire data set. Another example, right? So here you have a YOLO V4 object detector that is deployed on the camera, a dashboard of a car. And that same object detector, if we apply it to during dusk time or the evening, you see how badly it's performing, right? It's completely failing. So the question is now, what do we do? Do I have to drive around in the evening for hundreds of hours and collect data? Or can I use generative adversarial networks or GANs to perform the style transfer? So I'm starting out with my original data and I'm using a GAN to learn the representation to convert it to dusk or evening time data. And then if I train my YOLO on this data, I'm able to have better generalization and you can compare these two, right? So some of the techniques you're working on that you're learning about, these have real world applications and they are being used by industry. Similarly, if I have data and now I want to perform segmentation, how much data do I need, right? We all say the more data we have, the better chance we have of building an accurate model. So what we're also saying is you don't always have to record your data, but you can find some balance between data that's collected from the real world as well as data that is simulated or generated. And here we had, this is an environment, simulated environment that uses physics-based simulations and interactions so that you can model what are the different components. You can put in different cars, different kinds of pathways and so on, and you can supplement the data set that you have available for training. Okay. On the medical imaging side, has anyone here worked with NVIDIA's MonAI library? Yeah, one person? Yeah, so in MATLAB, we have support for the MonAI library. This can perform different kinds of segmentation. So you can do it for the entire body and then fine tune it on top of that, or you can pick out certain anatomy. On this side, you can see it's a very interactive way to perform segmentation and annotation, especially great when you're working with medical professionals and helping them to build models for their data sets. So that was it about data. I know I'm rushing through, but I just have a little bit of time. The next question I'll have is, what are my options for AI modeling? Okay. So I know that there are thousands and thousands of models out there, but let's say I'm an engineer working in MATLAB Simulink. How can I leverage models? The first thing to do is to build your own model from scratch. The second thing to do is to look at what the research community is putting out and bring in some of those models. When it comes to building your model from scratch, there is something called the Deep Network Designer. It's an interactive way, it's an interactive way for you to build your AI models. You can also do this using code, but if you prefer, if you're new to AI and you want to play around with the architectures and try things out, you can use the Deep Network Designer to do that. Okay. And after you've decided your blocks or your layers, you can go in and change your parameters. So we showed some of this yesterday as well. And in the interest of time, I won't show you the whole video, but yeah. Okay. So the first way was build your own model. The second was to bring in models from TensorFlow, PyTorch, Onyx, or even something called co-execution from Python, where if I'm working in MATLAB, I can call Python scripts. If I'm working in Python, I can call MATLAB scripts and apps, including all the apps I showed you before. How this works is either you can do it once again using code, or you can go back to the Deep Network Designer and you can import your PyTorch or your TensorFlow models from there. So in this way, you're able to leverage what some of the research community is doing. So this is my Deep Network Designer, and it's opening up, and instead of doing a blank network this time, I am going to import a PyTorch model and then use that in my further applications. Okay. So here's a snapshot, a very simple thing. I brought in an image classification network and then had it run on my webcam just to demonstrate how it's possible to bring in these PyTorch networks. Okay. So that's one way to do it, right? Where there are models that already exist, but you could also leverage models that exist on maybe something like Hugging Face. So anyone here uses Hugging Face? Yeah, a couple of you use Hugging Face. If you can always use co-execution to call in Hugging Face models. All you have to do is a py.dot and then call the right file. You can integrate that into your larger system, which uses, let's say, signal processing, control systems design, model-based design, and so on. Additionally, connection with LLMs. Anyone here uses LLMs? I think everyone here uses LLMs, right? So you can connect to LLMs, and these are either based on API calling, or you can have local models running through Ollama servers. Image generation, I've highlighted this because this is a topic that's generating a lot of buzz in automotive and aerospace. We have a lack of data. Here you have the runway and you have animals crossing, right? We don't have too much of data from the real world, but can we use generative AI to help build up a data set so we can now train models to identify these kind of scenarios? Okay. So that was about my AI modeling bit. My third question, and I'm sure all of you probably thought about this, is my AI model trustworthy? So trustworthy can mean a lot of things. And I know Professor Chandrasekhar mentioned something about AI models, right? That they have a black box nature. We know they work. We can't always explain why they work. So let's say I am a data scientist, an engineer, researcher, and I've built an AI model, and this is a black box AI model, which will go and sit in a larger AI system. It's going to make some decisions, and depending on who your stakeholders are, they may be business owners, medical professionals, customers, even from regulatory bodies. They're going to ask you questions about how do you explain this? Why did your model make a certain prediction? If instead I am able to somehow pass in feedback or some kind of explainability type of mechanism, I'm in a better position to explain why my model is making a particular decision. I'll give you a small story around this. So this is a company called Musashi Seimitsu. It's based out of Japan, and they are manufacturing automotive parts. So like a manufacturing company making 1.3 parts per month. Now, Japan is known for its very high quality of manufacturing and design, right? So they wanted to ensure that the quality of the product they're making is very high while still meeting the requirements, demand requirements. So what they wanted to do is, instead of using human beings to visually inspect each part, they now wanted to use technology, specifically a computer vision algorithm that is deployed on an edge device. So in this case, they used an NVIDIA Jetson board, I think a Jetson Xavier probably, and they trained their computer vision model to distinguish between okay and not good. Okay? But they take it one step further. So see what's happening here. This is a tag OK. And then you have this piece and it's showing a tag NG, which stands for not good. Not only is it telling you what is the classification, it's also telling you which part of the image is driving that particular class. Okay, so if you look at not good, you'll see a defect here, and this defect is picked up and highlighted by the explainability technique. Explainability can be used it's not limited to manufacturing. If you're working in biomedical, if you're working in UAVs, crops, whatever the application is, chances are you can incorporate some kind of explainability there. Okay. So here, for example, this is my colleague holding a coffee mug, and we've done image classification and it says buckle. So why is it saying buckle? Obviously because the model saying I'm focusing on this part of the image and therefore classifying it as a buckle. Similarly, when you have medical imaging data, I know this is it's actually a very low resolution picture. I've extended it for this purpose, but based on the cloudiness here, you can see that you're getting a prediction of pneumonia. A third example is when you have MRI data and you take a slice of it and you're using that slice, which you have as an image here, to identify what is the age of the patient. So the age of the patient is predicted by a network, but why is it given that age? Which part of the brain is telling me so is indicated here by the heat map. Okay, so I'm coming to a slightly I would say newer in terms of industry topic, which is around verification. So we know that if I've taken this picture of a bicycle and I know my network can distinguish that this is a bicycle, it's drawn a nice box around it, right? What we know, unfortunately, is that neural networks can change their classification based on very small changes that happen at the pixel value. Okay. So if I take this image of a bicycle, and if I introduce a perturbation, let's parameterize it by delta. What has my neural network done now? Right? It's actually classified this person as a pole, which is very wrong. As human beings, we can see that these are very similar images. The difference is the computer is seeing those imperceptible changes and it's making a misclassification in this case. So what we want to do, therefore, is to be able to characterize how a network is performing using methods of formal verification. So we take a bicycle here and we're giving it some kind of family of perturbations. We're saying randomly change. If I want to know how this bicycle will be classified, if I randomly change, if I change random pixels by 10% of the value, so let's say your values go from, you've normalized it and it's going from 0 to 1 pixel values. if I randomly change some of these pixels by 0.1, I can have millions of combinations of these changes, these randomly sampled changes, right? What I cannot do is pass all of these millions to my network for a single image. And imagine if I have a huge data set, how many times am I going to keep passing data through this network? In that case, we turn to a formal method of verification where we parameterize this perturbation, the random pixels by 10%. And then what we end up with is like a representation for a volume of these perturbed images now. Okay. A formal method of verification can then tell me, based on this perturbation, X% is still classified as the bicycle. Y% is unproven. We cannot say anything definitively. And Z% is violated because although it's the same image, more or less, with some perturbation, your network has now changed its final decision. Okay. So there is something called the Deep Learning Toolbox Verification Library, which allows you to do this formal methods of verification. And essentially what we're doing is taking our inputs, defining or parameterizing our perturbation, and then coming up with what are these three classes of, what are the three proportions. So when can I trust my network? What percentage of it can I trust? What do I have to be skeptical of? And what do I not trust? If something cannot be trusted, it's not the end of it. You will pass it on to a next stage of a human being checking it out or passing it to a different kind of algorithm or AI-based algorithm. Another important thing is the neural networks we train are trained on certain data, and that data is representative of a population. So we're essentially sampling that population or that distribution, and we're training a network for it to realize some kind of, for it to pick out some kind of patterns. But what if I get an image out in the field that does not belong to the distribution which I've trained on? I want my network to be able to tell me when an image is out of distribution. And this is important, especially when we're looking at fields where we're directly impacting human lives. This can be medical. This can be related to autonomous driving. It can be related to even stuff like face recognition and detection. So if my network, what I want to do is essentially have a network on the side, a detector, so to speak, which will tell me whether or not this is in distribution. Is this in distribution? Is it not in distribution? And a lot of this is characterized by the histograms that we get from running our data through these models. So again, like I said, the game is not lost, but if your detector is indicating that you're out of distribution, either you want to go and fine tune or retrain your AI model, or you may want to pass it on for human feedback. So my last point here is on, can I deploy my model to hardware? And I had discussions with some of you over the last few days where you were interested in taking your AI models and putting them on the edge. This could be low compute devices. It could be NVIDIA-based GPU devices as well. So in yesterday's session, we showed how to deploy a human object detection as well as pose estimation algorithm. And we had a volunteer who came in, we had two volunteers who came and interacted. We set up the Jetson here. That is what the Jetson looks like. And we were able to do real-time human pose estimation. So taking an algorithm, AI-based algorithm, and then putting it on the edge. Similarly, this is a very simple image classification example that runs on the NVIDIA Jetson. Again, it was hooked up to my webcam, which was connected to the Jetson, and then we just let it run. This was a very heavy model that we had deployed. So that's why you can see the frame rate is kind of low. It was really consuming a lot of the onboard memory. So when it comes to code generation, yes, the answer is yes, I can deploy my AI models to different types of target hardware. It can be industrial hardware, ARM processors, GPU devices like I showed you, microcontrollers, as well as FPGAs if you're working in this area. And the question is, if I have my model in MATLAB or in Simulink, if I have an AI model in MATLAB or Simulink, how can I possibly deploy it to these devices? Because to deploy it to an embedded device, you need to write your code in embedded C. To deploy it to your GPU device, you need to have a combination of C++ as well as CUDA code, your CUDA kernels. So the answer is through automated code generation. So we have automated code generation tools. We have the GPU coder that helps you generate CUDA code. We have the MATLAB coder that helps you generate your C++ code, HDL code generation as well. So depending on what your target hardware is, you can translate your algorithms to that code and deploy it or burn it onto your hardware. In the GPU coder, it gives you a performance analyzer as well that tells you where you have potential bottlenecks. So you may want to rewrite some of your logic. It tells you what is your CPU or your ARM processor versus your GPU-based resource consumption. And my favorite thing here is this bidirectional traceability. So on the left side, I have MATLAB code for fog rectification in a computer vision or in a camera that's deployed on a car. On the right-hand side, I have generated CUDA code. So if I want to know where my MATLAB code is going and translate into CUDA code, I can go and check it out in my traceability map. If I want to do it the other way around, this part of CUDA code, I don't understand what it means. What does it map to? I can click on it and it will direct me to which part of MATLAB, or if I have a Simulink model, which part of my Simulink model it maps to. So if you remember the Jetson screen grab I showed you, it was moving very slow. The reason being that I had a huge model. So sometimes you'll be in a situation where you've designed the best model you possibly can. And by the end of it, you're being told by your hardware team or your engineers that, hey, we only have so much memory. So you need to now optimize to that. You can optimize. There are two general ways to do it. The first is structural compression, where you look at pruning and projection. You either remove parts of the layers from your network or nodes from each layer. So if you have a fully connected layer, which nodes in there can be removed and they will not significantly impact your overall performance, as well as projection, where you're going from higher dimensional space to lower dimensional space. So that's structural compression, where you're working with the architecture itself. The second case is data type compression, where we're going from our floating point data to now fixed point data. And in that way, you're able to optimize and save on how much memory is being utilized. So you can run things at faster inference. Obviously, there's going to be a little bit of an accuracy trade-off here. So for example, on the top plot, you have memory versus 3 different types of applications. Original network in blue, prune network in red. Okay. So you can see memory-wise, classification, there's a decrease. Object detection, there is a huge decrease. And semantic segmentation, there's also a decrease. But when you look at the second plot, which tells you accuracy versus these 3 types of applications, you see that the accuracy is really comparable. It's so comparable to the fact that in industry, sometimes we are willing to forego this much if we're able to achieve this much. Okay. So if you're thinking of productizing, if you're thinking of submitting working proof of concepts to the agencies that fund you, I would strongly recommend looking at compression before you do deployment. Okay. So this is what your compression tools will look like. You get a map of which blocks are using what type of memory. And this is my current network. To what degree can I compress it using pruning, using projection, which layers are prunable, which are projectable, and so on. Similarly, on the quantizer side, these are all of my layers. Which of these layers can I apply quantization to? So with that, I come to the end of it, and I want to thank you all for your attention. I also want to point you towards a new generative AI offering that we have from MathWorks, which is a Copilot. So this is a free online, it's called the AI Chat Playground, where you can interact with your LLM. On the left side, generate code translated to the right side. So here we're looking at decision trees, for example. and then you can work with this Copilot in tandem. So if you want to check this out, go to MATLAB AI Chat Playground. You can find it online. It's free to use. So thank you very much. And if you have any questions around some of the stuff I talked about, if you want to get into the details or if you want access to yesterday's demo files, just send me an email and I'll be happy to share these with you. Thank you. Yes. Yes. PyTorch, you can do it using code or using the Deep Network Designer. So just Google MATLAB PyTorch interoperability or MATLAB PyTorch, you'll find the. It's from MathWorks. Yeah. Oh, that I am not sure. That you'll have to check. It will probably throw an error if it's not supported. So you run it through the quantization and you create your quantization objects. But then if it's not supported, it will probably throw an error for you while you're trying to do the deployment.
Also, I had one last question.
Sure.
Like, how do you compare with the TensorFlow Lite? Because the wide framework which are used for deployment, how do you compare this with that?
I haven't done any comparative studies, but I know that if you're working with certain functionality, hardcore signal processing or controls based, MBD based, then you'll typically be working in the MATLAB Simulink environment. And also this NVIDIA, the NVIDIA Jetson is one hardware I was targeting, but if you look at how do you generate code through Simulink, have you used Simulink? Simulink is a graphical based programming environment, mostly used for controls and model based design. So if I have an application for image classification in Simulink, I'm going to build that application graphically, taking an input, image pre-processing, AI modeling. Then I'll do something like calculating my frame rate, getting my classification output, and displaying both of these on my devices, edge devices display. So that's what I did with the Jetson. And the Jetson input and output boards will come in for the image, input and output blocks will come for image capture and for displaying on the hardware. Now let's say I want to take that same model and deploy it to a Raspberry Pi. What I can do is remove the Jetson blocks on both ends and bring in the Raspberry Pi blocks. I don't have to change anything else. It will automatically adapt to the hardware. It will automatically realize what kind of code you need to generate and deploy the code for you.
Thank you.
Sure. Yes, please. Yes.
So it will always be there, or we can do something to recover the accuracy?
Typically that will be there, but one option you can look at. So sometimes when you do quantization, you'll notice more of a drop. What we've noticed is not quantization, but after projection and pruning, you can look at fine tuning your network. So you'll have to experiment a little bit with the combinations of the compression and fine tuning. But like I showed you for certain cases, object detection, semantic segmentation, the performance was comparable. If you want more details, reach out to me. I can give you a detailed analysis of this.
How many modules are there for AI?
Modules as in, sir?
MATLAB, they have different modules.
Toolboxes. Okay, right.
For AI?
Yeah.
Only one app?
Right. So for AI, so before I answer that, I'm just curious, are you from, which institute are you from? ISI. Okay. Right. Because a lot of universities, IIITDM, IITs, even across the country, they have access to all the tools in MATLAB. So when it comes to AI, I would say the entire suite of tools you need would be if you're doing machine learning, deep learning, computer vision. If you're interested in AI for medical imaging, then the medical imaging toolbox as well. And for coding, deploying the code, you will need the coder tools for that. So embedded, HDL, and GPU coder. You're welcome.
Any more questions?
Madam, you use the phrase called formal verification, right?
Yes.
But there you have not used mathematical proof, right? Usually formal
It is
verification.
mathematical based. I just didn't show all of the details, sir.
So will you prove like what we do in software engineering?
Yes, that's actually where it came from. So because we work in industry, like if you take aerospace industry, for example, or automotive industry, you typically have the V cycle for software development, right? You start with requirements, system level requirements, unit testing, system integration testing, and then finally deliver, right? But the problem was when the automotive industry and when the aerospace industry started to look at including AI, then they realized that V cycle is not going to work.
Right.
What they're actually working on is the W cycle now, right? So the W cycle has the bottom half of it is dedicated to learning process management, data management, verification and validation. And that's where the formal methods of verification and validation come in. It was designed specifically for that purpose.
So you'll make some theorem statement and prove.
Yes, it is a mathematical, it's a rigorous formal verification.
Okay.
Any more questions?
Yes, sir. So explainability, at least the methods I showed you, right? These are post hoc methods of explainability. They are applied after model training has happened, and the ones I showed you do not come into picture while you're training the model. What you're essentially trying to do is map that relationship between the inputs and outputs, regardless of what happened during the training process. Now, some networks, I wouldn't say deep learning networks, but some, let's say, machine learning algorithms are intrinsically more explainable because of their nature. If you look at decision trees, linear regression, they're inherently more explainable. But when it comes to deep learning, especially vision-based and more complicated ones, post hoc methods are predominantly used. That is also based on the domain. If you want, you can go online and look at, we covered this yesterday. We showed people how the explainability methods, what are the different types, how do you implement them. So you can just go and look it up online, MATLAB explainable AI. It will point you towards, there are hundreds of examples that walk you through deep learning, and like maybe about 15 or so that specifically focus on AI, explainable AI. If you have questions, like I said, please reach out. Yeah.
Okay. So let's thank the speaker. Thank you, Nikita, for
Thank you.
comprehensively walking us through the AI and how we can seamlessly integrate MATLAB with applications. So I request Professor Umarani ma'am to felicitate the speaker.